Hello everyone, and welcome. I'm excited to start today's presentation on chemical oxygen demand, or COD for short. This slide introduces our main topic and sets the stage for what we'll explore. Over the next few slides, we'll dive into what COD is, why it matters, and how it's measured. Let's get started. Let's walk through the key points on this slide. First, we start with the introduction, which is essential to set the context for what we're about to discuss. Then, we move on to the requirements. These are the specific needs or criteria that our solution must meet. Recognizing these helps us ensure our approach is targeted and effective. Next, we look at the solution preparation phase. This is where we gather all the necessary tools, data, and insights to develop a robust approach. Following that, the process itself is crucial. It's the step-by-step methodology we follow to implement our solution. The formula represents the core calculation or model that underpins our approach. It's the mathematical or logical foundation that guides our analysis. Then, we arrive at the results, which are the outcomes of applying our process and formula. Finally, the contents encapsulate all these elements, providing a comprehensive overview of the entire framework. Connecting all these points together helps us understand how each component plays a vital role in achieving our overall objective. This slide essentially maps out the journey from understanding the requirements to obtaining meaningful results. Let's talk about the concept of organic matter contamination, or the overall organic load in water. Essentially, we're measuring how much organic material is present, which can impact water quality. One important way to do this is by using the chemical oxygen demand, or COD, test. This test tells us how much oxidizing agent is needed to break down the organic matter under controlled conditions. The result is expressed as oxygen equivalents, giving us a clear idea of the organic load. There are two main methods for determining COD: the open reflux method and the closed reflux method. Both methods involve reacting the organic and inorganic matter with a strong oxidizing agent, specifically dichromate ions, in acidic conditions. The chemical reaction produces carbon dioxide, water, ammonia, and chromium ions in different oxidation states. During the experiment, we determine how much excess dichromate remains after the reaction by titrating it with ferrous ammonium sulfate, or FAS. The key reaction here is between Fe2+ ions and dichromate, which reduces the dichromate to Cr3+ and oxidizes Fe2+ to Fe3+. This titration allows us to precisely measure the amount of dichromate that was consumed, and thus, the organic load. So, in summary, COD testing is a robust way to assess organic contamination in water, helping us understand pollution levels and manage water quality effectively. Today, I'll be talking about the essential equipment and chemicals we need for our analysis. First, we have the COD digestion apparatus, which is crucial for breaking down organic matter in our samples efficiently. Alongside that, we need a titration unit, which allows us to perform precise titrations to determine the concentrations of various substances. Moving on to chemicals, we rely on potassium dichromate as our primary oxidizing agent. Mercuric sulfate is important for removing interfering substances, ensuring accurate results. Ferrous ammonium sulfate acts as the reducing agent in titrations, while potassium phthalate is used as a standard solution for calibration due to its stability. Sulfuric acid is essential for maintaining the acidic environment needed during digestion and titration. Silver sulfate helps in the precipitation process when necessary, and ferrin indicator is used to signal the endpoint of our titrations clearly. Finally, under requirements, I want to emphasize that having all these equipment and chemicals ready and properly maintained is vital for the accuracy and reliability of our tests. These components form the backbone of our analytical process, ensuring we obtain precise and consistent results throughout our work. Now, let's look at how we prepare the key solutions for our titration. First, we have the potassium dichromate solution. We add about 500 ml of distilled water to it, ensuring proper dilution. The potassium dichromate we use is of primary standard grade, and it's been dried at 150 degrees C for 2 hours to ensure its purity and stability, which is crucial for accurate measurements. Next, we prepare the sulfuric acid solution. We take 167 ml of concentrated sulfuric acid and add 33.3 grams of silver sulfate. After dissolving these, we cool the mixture to room temperature and then dilute it to a final volume of 1,000 ml. This step ensures we have a consistent, concentrated acid solution for our reactions. Moving on, we prepare the ferrous ammonium sulfate solution. We dissolve 39.2 grams of ferrous ammonium sulfate, specifically Fe, NH42, SO4, 6H2O, in distilled water. To this, we add 20 ml of concentrated sulfuric acid, then cool the solution before diluting it to 1,000 ml. This solution will serve as our standard reducing agent. Finally, we have the ferrine indicator, which is ferrous 1,10-phenanthroline sulfate. While the slide doesn't specify its preparation, it's important to note that this indicator will be used to signal the endpoint of our titration, turning a distinct color change when the reaction is complete. All these solutions are fundamental to our titration process. They need to be prepared accurately to ensure reliable and reproducible results. Let's walk through the process step by step. First, take a culture tube with distilled water, which is prepared as a blank, and another tube with your sample. Then, measure out about 20 ml of your sample into the tube, adjusting the volume as needed. Next, add 10 ml of potassium dichromate along with a pinch of mercuric sulfate. After that, pour in 30 ml of sulfuric acid solution. Once these reagents are added, the tube needs to go into the COD digester and stay there for about 2 hours at 150 degrees Celsius. This digestion step is crucial because it breaks down the organic matter in the sample. After digestion, allow some time for the solution to cool down to room temperature. Once cooled, transfer the solution into a conical flask and dilute it with 60 ml of distilled water. Then, add 4 to 5 drops of ferrine indicator, which will help us identify the endpoint during titration. Now, titrate this solution against a standardized ferrous ammonium sulfate solution. As you titrate, you'll observe a color change, starting from green to sea green and finally turning into a red wine color. This indicates the endpoint has been reached. Be sure to note the volume of ferrous ammonium solution used, as this reading is essential for calculating the chemical oxygen demand. This process allows us to assess the amount of oxygen required to oxidize the organic matter in your sample, which is a key indicator of water quality. Now let's look at the formula for calculating COD in milligrams per liter. The equation is COD mg/L equals the difference between A and B, multiplied by M, then by 8,000, and finally multiplied by the dilution factor, divided by V. Here, A represents the volume of FAS used for the blank, measured in milliliters. B is the volume of FAS used for the sample, also in milliliters. M is the molarity of the FAS solution, which tells us how concentrated our titrant is. The number 8,000 is a constant derived from the milliequivalent weight of oxygen times 1,000 ml per liter, ensuring our units are consistent. V stands for the volume of the sample we are analyzing. This calculation is key because it translates the titration data into a straightforward measurement of chemical oxygen demand. Remember, the core idea is that by measuring how much titrant is used to reach the endpoint, we can determine the amount of oxygen consumed by the sample, which reflects organic pollution levels in water. Connecting this to our overall theme, understanding and accurately calculating COD helps us assess water quality efficiently, guiding environmental management and treatment processes. Let's take a closer look at what COD levels tell us about water quality. When the COD is less than 20 milligrams per liter, it indicates the water is very clean, with minimal organic pollution, and it's safe for use. Moving into the 20 to 200 milligram range, the water becomes moderately polluted. Here, you'll often find domestic sewage, which signals some organic matter presence but not necessarily dangerous levels. As the COD increases further, between 200 and 500 milligrams per liter, the water quality drops to poor. This high organic load can be harmful to aquatic life, stressing ecosystems and reducing water health. When the COD exceeds 500 milligrams per liter, the pollution is considered heavy, making the water dangerous for aquatic organisms, and it requires intensive treatment before it can be safely used or discharged. It's also important to note that for drinking water, the COD level should be less than 10 milligrams per liter to ensure safety and quality. Monitoring these levels helps us understand the extent of pollution and guides us in managing water resources effectively, aligning with our overall goal of ensuring clean and safe water for all.